This represents a neutral atom in electrical balance. Earlier, we saw how an outside force can break an electron away from an atom and start an electron chain reaction, an electric current flow. One way to provide that outside force is by use of a magnet. It was proved with iron filings that a magnet has magnetic lines of force which connect its poles. For simplicity, let's consider the effect of this magnetic field on a single electrically neutral atom. Now, we move the magnet so that the magnetic field strikes the atom, supplying energy which forces an electron to leave its atom and become a free electron. The result is a sort of electron chain reaction. In a substance such as a length of wire, electrons are normally moving in all directions. But when a magnetic field is passed through the wire, several electrons are forced from their atoms and move in one direction. Now, in studying electricity, we're mainly interested in the movement of free electrons. So, for convenience, we'll look only at the action of electrons in the wire. When the magnetic field sweeps down across the wire, electrons move in one direction. When the magnetic field sweeps up across the wire, the electrons move in the opposite direction. This movement of electrons in either direction constitutes an electric current flow. If we move the magnetic field more slowly across the wire, fewer electrons are affected in a given period of time, and the electric current flow is decreased. And when we stop moving the magnetic field, the electric current flow stops, and the electrons again move in all directions. If this wire is connected to a meter, we find there is no electric current flow. When the magnetic field is moved down, this meter shows current flow in one direction. If the magnetic field is moved up, the meter shows current flow in the opposite direction. We can change the amount of electric current flow in several ways. Move the magnet faster, more current flows. Use a stronger magnetic field, still more current flows. Now coil the wire so that several turns are in the path of the field. Again, the current flow is increased. Stop moving the magnet, current flow stops.
Voltage can be thought of as the height of a mountain. Rocks at higher elevations can do more damage. The same is true with voltage. The height of the mountain tells you the energy of each falling rock. The total power is the height of the mountain times the number of falling rocks. Similarly, the voltage is the energy of each charged particle. The total power is the voltage times the number of particles. The number of particles is called the current.
Measure the value of this resistor. So I'm going to take my battery. I'm going to take the positive terminal. I'm going to connect it to an ammeter. I'll call A. And connect that to one end of the resistor. And I'll take the other end of the resistor and I'll connect it to the negative terminal of my battery, minus, plus. Let's presume that the battery is a 1-volt battery. And I'm going to take my voltmeter and I'm going to put it directly across the terminals of the resistor. We'll call this V for voltmeter. And I'm going to take a series of readings. Now I put the voltmeter right across the resistor terminals because this wire is going to have a little bit of parasitic resistance. And I don't want to measure that. And the battery will have some series resistance associated with the battery. So by putting the voltmeter right across my unknown resistor, I don't measure these parasitics that are in the circuit. Let's presume that I read 1 volt on my voltmeter. So the parasitics are very small. And I measure 1 amp. 1 amp of current flow in this resistor. So I can calculate the resistor by a very simple equation. Resistance is equal to the voltage across the resistor divided by the current I going through the resistor. This is called Ohm's law, and we'll talk more about Ohm's law in the future. So in this case, I can calculate my resistance. R is equal to 1 volt across the resistor divided by 1 amp through the resistor is equal to 1 ohm. We use the Greek symbol omega to denote ohms. So that's rather simple. Let's take a battery that has a voltage V, and we'll connect the plus terminal to a resistor, and we'll connect the negative to the other end of the resistor. So this is negative terminal, positive terminal, resistor R. Let's ask ourselves, what is the current in the circuit? The current flows from plus to minus. Now, in reality, the charge is really negative and flows from minus to plus. But the conventional current is always assumed to flow from plus to minus, because when they came up with that convention, they didn't know that electrons were negative charge carriers. So your circuits will work just fine if you think of current as flowing from plus to minus. So let's get back to Ohm's law, and let's see if we can figure out what current is. How does current relate to voltage and resistance? If I increase the voltage in the circuit, I've increased the electrical pressure. It's like the pressure in a garden hose that's filled with water. As that pressure increases, I have more water flow in the hose. So as voltage increases in this circuit, I have more current flowing. So there's a direct relation between current and voltage. So voltage goes in the numerator, which means as voltage increases, current also increases. But as resistance increases, we have more resistance to current flow. So as resistance increases, the current decreases. So there's an inverse relationship between resistance and current. So resistance goes in the denominator.